Okay, let's start. Good morning. We have two items remaining from this orthogonality business. One of them is this QR factorization, and the other one is the axiomatic approach to inner products. So let's start with this QR type factorizations. Of course, as usual, there's a bunch of different varieties of this idea. So when you sort of do row reduction in a controlled manner, and if you put your elementary matrices that correspond to your row operations in a certain way, or if you choose certain matrices for those, you get an LU type factorization. If you do the same thing in the context of Gram-Schmidt, you get a QR type factorization. Okay? So the idea is that you start with an m by n matrix A, and what you want is you want to be able to write A as Q times R, where Q is essentially an orthogonal matrix and R is essentially an upper triangular matrix. Now, in general, this middle dimension S is, so depending on the type of QR factorization you want to do, it changes, but there are a couple, so that's not that important. What is important is that at least the columns of Q are orthonormal. So you want that to happen. And the reason why this is the case is perhaps more important than the QR factorization itself. So let's look at a specific case of the situation where A has linearly independent columns. So specific case, special case. And A has linearly independent columns. So if I were to write A like this, so the first column, let's say, is A1, second column is A2, and so on, and I said that A is m by n, which means that I'm going to have n columns. So each of these vectors I can imagine to be in Rm, and I have n of them. Now, based on this, I can immediately say that the column space of A is n-dimensional, right? Because the columns now of A is going to constitute a basis. So this is a basis for the column space. Column space of A is a subspace in Rm, which means that n, which is the dimension of the column space, rank of A, is not more than m. Right? I also have that if I want it. So let me write it here. It's a subspace of this. And n, which is the rank of A, cannot be larger than m. So let's apply Gram-Schmidt to this subspace relative to this basis, right? You can do this. Applying the Gram-Schmidt algorithm to the subspace column space of A and that basis to the subspace with basis A1 to AN, and then orthonormalizing it, or normalizing the vectors. One obtains an orthonormal basis for the column space. And let me write it like this: q1, q2 dot dot dot, qn of column space of A. And recall that these bases are related in a certain way, namely that their flags are the same. Meaning that if I were to take the first, let's say, k vectors in this basis and look at the span inside the column space, that span would be the same as the span of the first k vectors in the other basis. The flags would be the same. Meaning that for any index I, or for any index k, span of A1 to AK would be the same thing as the span of Q1 to QK. Okay, if this is the case, then I can think of it like this. AK, right, this vector, is in the span of Q1 to QK, which means that I can write AK as a linear combination of these guys. So let's write it like this. So R K1 Q1 plus R K2 Q2 plus dot 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 plus R K K Q K. Now if I want, I can keep going, of course, because AK is in the column space and this guy is a basis. But you know, the remaining elements are always going to have 0 as the coefficient because of this flag preservation property. So maybe I could write it like this. 0 times, let me write it like this. R K, K plus 1, Q, K plus 1. Then R K N, Q N, but each of these are going to be 0. After this, all of them are going to be 0. So and I know for sure that this guy is non-zero, right? Because this is linearly independent. So this span has k dimensions, and so is this. Okay? So I don't know what this number is. I know, though, that it is non-zero. Okay? Well, if this is the case, yeah, so recall from, I guess, week 1, then I can write AK, since it is a linear combination of Q1 to Qn, I can write it as a matrix whose columns are Q's times a vector whose entries are R's. So that is equal, maybe I can write it there. So this is equal to Q1, Q2, Qn times R K1, R K2, dot, 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 R Kn. I said that after a while this becomes 0, but still this is perfectly valid. Well, if this is the case, certainly if I were to consider A itself, I would get this. N. You see, I'm always going to use the same matrix first. The matrix whose columns are generated, are created by Gram-Schmidt. But then here, you see this vector is going to change. R11 to R1 n, R to 1, dot, 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 to r to n, and then r, finally, n1 to r and n. Okay, so this was an m by n matrix. This is also an m by n matrix. It has n columns, and each of these vectors are in Rm. And certainly, this is n by n. It's a square matrix. Okay, and the idea here is that, you see, if I were to plug in k equals 1, I'm only going to see R11 to be non-zero, and all others are going to be 0. Okay, so really, this is an upper triangular matrix with non-zero entries on the diagonal. And this is a matrix whose columns are orthogonal. So call this Q, call this R. Then I have that Q is it has normal columns. And this guy is upper triangular. And on the diagonal, it has non-zero entries. Let me just say it is invertible, because we know that the determinant of an upper triangular matrix is the product of the diagonal entries, which is the product of the eigenvalues. I'm saying that none of the eigenvalues is 0. That is equivalent to saying that it is invertible. Now, if you were to start with a matrix that is whose columns are not linearly independent, you can still do this, but you need to keep track of the pivot columns and so on. It gets slightly more complicated to write it down. And this is the version that is written in the book, so I just wanted to leave it at that. But there are more complicated versions of this. Sometimes you want to sort of like turn this into a square matrix too, and so on. So some people call this, the one that I wrote here, the reduced QR factorization and everything. And if you want, you can also create your orthogonal matrix on the right-hand side instead of the left-hand side, blah, blah, blah. There's a bunch of variations depending on the situation. But this was something that I wanted to mention. Any questions about this? Yes?
So Q is orthonormal. That pretty much means that in whatever vector space, it's just like a matrix whose columns are like 1, 0, 0, 0, 1.
Essentially, yeah.
So does that mean that R is kind of the core identity of A?
Yeah, that's, I would say it's the other way around this time. Because now, the common interpretation seems to be, so because this R is upper triangular, it's sort of like a row reduction type of matrix. It's an elementary matrix almost. So what you want to say is that A is basically orthogonal up to an error.
Okay, maybe you can help me understand something.
Yes.
I got so insecure last night.
Yes.
I was trying to work on a problem because I do not understand spectral data.
Okay.
And I was doing like reduced row echelon form, right?
Okay.
So like that's where we use the entries to eliminate other entries.
Yes.
And I got to this place, like I was working in 2 by 2, the entries 3, 2, 0, 1, and I'm like, you can obviously use the second 2 to eliminate the first 1, and eventually get to reduced row echelon form, you scale it, you get the identity matrix, and then it's like, well, wait, I thought that if you got reduced row echelon form, it's supposed to be like the core idea of the matrix.
Well,
scalar.
yeah,
but it's not.
Exactly. The reduced echelon form breaks the spectral data.
Is that like?
It breaks the spectral data.
So why did I think that reduced row echelon?
Because I told you that, okay? I mean, in week 2, like that's all I could say, okay? In terms of column spaces, null spaces, ranks and stuff, LU factorization is good, but not for spectral data. That's why we did start with eigenvalues. That is true. How does spectral data get preserved? The standard way is if you can find if 2 matrices are similar to each other.
So I'm saying the core idea of the matrix. Would you say that's like the specter of the matrix? Like, is that why it's called spectral?
I would say so.
It's
I would say so.
Like that's like the fundamental idea.
Yeah.
Okay.
Because here's the thing. we kind of mentioned this. If you take a square matrix, a random square matrix is going to be invertible. Now, when you do LU factorization, it's just going to tell you that, so that its reduced echelon form is always going to be identity for a square matrix. So it's just telling you, oh, you know, you can use lower triangular matrices, blah, 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 to split your matrix. But that is not really telling you too much information about what the powers of A look like, for instance. So next week, we're going to discuss this application in the context of dynamical systems a little bit. It is important to be able to take powers. And really, LU factorization doesn't really help you with that much.
Why are, I don't know if you guys mind the tangent.
No, good.
Why are you, so like I was watching a lecture by the Hilbert-Schmidt, and he mentioned the K powers idea.
Yeah.
It's like, it's just a specific thing to mention. Like how come we're mentioning, like on the homework, there was a problem, like find the 500th power.
Well, okay, so it's like, so in dimension 1, taking the kth power of a matrix is just taking the power of a number. So if you're trying to, you know, compute compound interest, for instance, you just take the power of a number. Now, if your system is more complicated, and typically it is, now you need to, so now you have a couple of quantities that sort of relate to each other. And so you still want to compute the powers of the matrix.
Sure, it would be nice if you could just get the eigenvalue.
Yes. Yes.
Okay.
Yeah. Yeah. Are there any other questions possibly related to this stuff?
So what does it mean to like be an upper triangular matrix if you're not square?
Yeah, I know. I didn't want to say this, but essentially, so okay, in terms of entries, so the ijth entry I want to be 0 if I is larger than j. Yeah. For, okay, that's what I mean. So for instance here, this entry is the 2, 1 entry. Oh, I wrote it wrong probably. So this should be 1, 2, of course. 1, give me a second. N2, N1, 1N, N. Okay. So here, I is 1, J is 2. You see, J is larger. This is fine. But if it's the other way around, if the first entry is larger, that means that you're under. So maybe it's not square, so you have more entries down here. I want them to be 0 as well. Yeah. Upper triangular like. So the idea is that you start with the matrix, you apply Gram-Schmidt, that gives you an orthonormal or orthogonal matrix. You normalize, orthogonal basis. You normalize them to get an orthonormal basis. You put those basis vectors into the columns of a matrix. That's going to be your Q. Whatever is left is what I mean by upper triangular. Yeah. Any other questions? Okay.
Maybe a bunch of stuff.
Yeah, I mean, solving systems, but also it is related to a method called the QR method. And that allows you to find eigenvalues. So you sort of like put this into a more sophisticated algorithm, let's say. You keep iterating this algorithm, and asymptotically, your matrix converges to something called the Schur form. That's too complicated. We're not going to discuss it. There's an exercise in the book if you're interested in these kind of things, but it just allows you to compute things faster, essentially. Yeah. So now the axiomatics. An inner product space from an axiomatic point of view. So let's, as before, when we discussed the vector space, the definition of a vector space from an axiomatic point of view, let's first write down the important properties of this dot product or inner product. Of inner product in Rn. So first of all, so this inner product takes two vectors and produces a number, right? And if I were to fix the vector in the first entry, now with respect to the second entry, it's going to be a linear transformation. So I can write it like this. So v and then w1 plus w2 inner product, right? This is equal to v against w1 plus v against w2. And if I were to fix again the first entry and scale the second entry by some number, I can take that scalar out. So that is to say, if I were to fix v into the first entry, you see now I have a linear transformation from Rn to R. We can think of it this way. Of course, it doesn't matter where I do this. I can fix the second entry and do the same things with the first entry. Let me write those down. And again, I have this. C times v against w is the same thing as c times v against w. We have two more properties that are also important. One of them is that the inner product of v against w is the same thing as the inner product of w against v. So I can switch the orders here. So this is the first box. The second box is that I can switch orders. V against W is the same thing as W against V. And then the third property is that if I were to take a vector and take its inner product with itself, I'm going to get its norm squared. So it's going to be a positive or non-negative number. Right, so this is norm squared. So should be like this. And that the only time this is 0 is when v is 0. There are no other vectors for which the inner product with itself is 0. Okay. Now the reason why I split these properties is because we have seen throughout this class different things that allow you to combine two vectors in some vector space that satisfy some of these ideas. So let's sort of go through the taxonomy of these a little bit. And this is essentially the start of what is called multilinear algebra, or tensors. Multilinear or tensor algebra. And I'm not going to write, even when I'm using abstract vector spaces, alpha for the addition and sigma for the scalar multiplication, I'm just going to pretend that everything is, I'm just going to use the plus notation and just write the number next to it for scalar multiplication. So first of all, the things that satisfy that first thing is called bilinear. It's not a linear transformation, but it is linear relative to each of its arguments. So let's write it like this. T from, let's say, V, W to U. V, W, and U are three vector spaces that are abstract. I'm going to call it bilinear. If for fixed V in V, so now I fix the first entry so that this now is a transformation from W to U. I want that to be linear. And for fixed W, if I were to fix the second entry now, I want that to be linear from the first argument to U. Okay? So that is to say that this box is saying that the inner product is bilinear. Bilinear. If you had three inputs, three vector inputs, it would be trilinear. If you had n vector inputs, it would be n-linear. Okay? So what are different examples of bilinear transformations that you're comfortable with? Well, if you were to take two numbers, multiply them, that's bilinear. Multiplication is not really a linear transformation, but it's a bilinear transformation. So is matrix multiplication, for instance. So is taking determinants for 2 by 2 matrices. So, examples. Number multiplication, right? So xy goes to x times y. Matrix multiplication. Now my vector spaces are spaces of matrices of appropriate dimension, of course, and I send it to A times B. This is not a linear transformation, but it is certainly bilinear. Commutators or determinants. I feed to it two vectors, two-dimensional vectors, and send it to the determinant. So it just gives you a number that's bilinear. Commutator of two matrices. Take two matrices and send it to their commutator. Okay? These are some examples that you're already familiar with that are bilinear transformations. Second one is called symmetry. A bilinear transformation is called symmetric if this happens. It's called antisymmetric if, when you switch the places, you get a minus. So that's one definition. Other definition, a bilinear transformation T, but this time I'm taking the input to be the same vector space instead of V and W, taking them to be the same, and I'm going into somewhere else. W is symmetric if T of V1, V2 is the same thing as T of V2, V1. And of course, if you had 3 copies, for instance, for trilinear transformations, you would want any permutation of these 3 vectors. And it's called antisymmetric if you pick up a factor of minus. Antisymmetric. Or alternating is another way of saying this. If T of V1, V2 is minus T of V2, V1. Okay. Now, certainly, number multiplication is a symmetric bilinear form, or bilinear transformation. Matrix multiplication is not symmetric, right? Because we know that AB is not equal to BA, but also it's not minus BA. So it is neither symmetric nor antisymmetric. Determinant, you see, is an antisymmetric bilinear transformation, and so is the commutator. Nor anti. Determinant is anti. Commutator is anti. Now, what do I mean by this, for instance, when I say the commutator is antisymmetric? I basically mean that if I were to look at A bracket B, or A commutator B, and B commutator A, certainly it's going to be minus the other one. Right? So this is literally BA minus AB, which is the same thing as minus AB minus BA, which is the same thing as minus A bracket B. Okay? And what do I mean by when I say that the determinant is anti-symmetric? Well, if I were to take two-dimensional vectors, put them in a matrix so that I have a square matrix, look at the determinant. Well, if I were to switch the columns, right, I would pick up a factor of minus when I'm computing the determinant. That's what that means. So here I'm saying that the inner product is symmetric. And finally, this is called positive definite. Let me not write that down. I hope you can imagine how that would look like. What is an example of a symmetric bilinear form or bilinear product that is not positive definite? Well, one example of this that is very important is the so-called Minkowski metric. And this is what you use in the context of special relativity. So let me write that down as an example. So this is important. Minkowski product. So you take two vectors in R4, right? So that's going to be your space-time. So let's say that T1, X1, Y1, Z1. So T is supposed to be your time, right? And if you were to take another one, you define their inner product to be basically the same as what you would expect, except that this has a minus in front when you multiply. And all others are the same. So T1, X1, Y1, Z1, inner, T2, X2, Y2, Z2. According to Minkowski, let me put that subscript there, equals, I'm just going to write down the standard inner product. Except here you have a minus. That's all there is to it. And this gives you special relativity somehow. Just putting this minus here. So there's a minus here. Only this has a minus, everything else has a plus. So this somehow is just enough math to distinguish time from space. Gives a flat space-time, which is the main space, let's say, in the context of special relativity. There's also general relativity. For general relativity, you require that the space is not flat, it is curved, and that is more complicated. But special you can do using just linear algebra, essentially. Okay? So if I have a vector space, how can I define an inner product on it? I can say that an inner product of my on my vector space is a bilinear or symmetric bilinear positive definite form. That's the definition. Let me write it there. So this tensor algebra or multilinear algebra is the core of modern geometry. Modern being, it's been that way for the past, basically, 130 years probably. So let me say that in this context, there is no mention of gravity. Okay, so objects don't bend the space-time and so on. This is flat. Doesn't tell you anything about gravity. But like for local charts, let's say, this is sufficient. It turns out. So definition: let V be a vector space over the field R. For complex vector spaces, the definition is slightly more complicated. Let's not get into that. An inner product on V is a function. Let me write it like this. So these bullets say they're like placeholders. I get to put things in there. Is V from V to R such that is, let me say, symmetric, bilinear, and positive definite. That's the definition. How do you come up with inner products? Well, you can use this idea of transference of structure, which says the following. Oh, maybe let me give an example where this would be useful. If I were to take a space of matrices, there's a standard inner product on it, and that's called the Hilbert-Schmidt inner product or the Frobenius inner product. So example, let's say that my vector space is M by N matrices so I need to take two matrices of the same dimensions M by N, and I need to associate to them a number in a way that satisfies these properties. I'm just going to put here F for Frobenius. So define it like this. A against B, I want to be this. So I want to first multiply. I can't multiply in general because you see N doesn't need to be equal to M. But if I were to take the transpose of one of them, then multiplication is valid. This is not a number though. It is bilinear. It's not symmetric. And it's not giving me a number. But what I can do is I can look at the trace. This gives you, it turns out, an inner product on the space of M by N matrices. And this is called the Frobenius inner product. Frobenius or Hilbert-Schmidt. Same Schmidt as the Gram-Schmidt, which apparently was a Nazi, as I understand, but just learned it this morning. Inner product. Okay. It's a verification, of course, to verify, to deduce that this is indeed an inner product. It satisfies these properties, but it is true. And let me say that once you have an inner product on your vector space, as usual, you can define a norm and distance. And you can talk about angles between vectors. Okay? Angles, norms, lengths, that is, and distances. So now, with respect to this inner product, we can talk about the angle between two 5 by 7 matrices. We can talk about what it means for two matrices to be orthogonal. Okay? So this is very powerful, and you can also talk about what it means for two matrices to be close to each other, right? Because you can talk about distances, which means that you can say, oh, this matrix approximates that other matrix. Very nice. Perhaps let's compute this expression to see what it is. So for these kind of things, it's better to use this sort of index notation instead of writing out the matrices and so on. It's slightly faster to write these down. So you can write it like this. Okay. So A against B, inner, according to Frobenius. That's the definition. Now, what is this matrix? This matrix is M by M, right? Because A is M by N, and B is M by N as well, which means that B transpose is N by M. So A times B transpose is going to be M by M. its trace is the sum of the diagonal entries, so I can just set up a sum where I runs from 1 to m of the diagonal entry of AB transpose. But what is this? I had written this formula a long time ago. We haven't used it that much, but I need to have another loop inside this that runs through the columns and rows appropriately. One to, so I want to run through the row of A, and rows are n-dimensional, so this is going to be 1 to n, A, I, K, and then B transpose Ki. But B transpose Ki is the same thing as B Ik. Okay? So what does this mean? In order to compute this inner product, all you need to do is to look at your matrix, two matrices, and look at this entry, which is the 1, 1 entry, multiplied by this entry. Okay? Okay, so that's the first term. Then look at this, multiplied by that. Add it to what you had before, and so on. Okay? So let's perhaps write a numerical example. One, two, three, 2, 1, 0 against 2, 5, 6, 0, 0, 1. This is just going to be 2 plus 10 plus 18, and then 0 plus 0 plus 0. So that's that. So that gives me 20, 30. Okay, this is how you do it. And more generally speaking, here's another way of coming up with inner products. If you have an inner product space, so say T from V to W is an isomorphism, and say that on W there's an inner product. Then you can transfer the structure using T, which means this. Now you can define a new inner product on your first space like this. Let's say x against y relative to t is just going to be this. Look at the images, so t of x and t of y. That's going to give you two vectors in W. Now take that inner product, their inner product using this. So this is the one that I had already. Okay. I'm out of time, but I wanted to mention that also, of course, you can apply the same idea in the context of function spaces. And for instance, if you want to interpolate some data points using polynomials, so that is essentially related to a certain inner product. With respect to that inner product, there's an orthonormal basis for your polynomial space, and so on. And likewise, in a different context, these cosine of nt and sine of nt turn out to be an orthonormal basis for a certain inner product on function space. And the coefficients of your vector, which is a function, and that function space turn out to be nothing but Fourier coefficients, if you know something about that. Okay, but this is all I wanted to say. Tomorrow, we're going to start talking about symmetry. So And this idea of positive definiteness is also, again, going to show up. Okay? Thank you. I'll see you tomorrow. Okay. Let's start. Good morning. So today, finally, we're going to start talking about the spectral theorem. I wanted to give some more definitions before. So if I have an inner product space V over the real numbers, really, because we're not really considering complex inner products, it is slightly different. And if I have a linear transformation from V to itself, then I can define this no transformation T star from V to V, and that's called the adjoint of T. And that is defined by this equation. For any V and W, certain I can apply T to one of these vectors and then take the inner product. So that gives me a number. I want T star to be defined so that this equation holds no matter what V and W are. It is somewhat non-trivial to see that indeed this equation does define a unique transformation T star, but it does. That's one of the reasons, one of the underlying reasons why this notion of an inner product is defined the way it is. And I'm going to call a transformation self-adjoint if its adjoint is itself. Okay, T star equals T. Of course, in the context of matrices and tuples as vectors, the adjoint is nothing but the transpose. Okay. Because if I were to start with this, right, so this is the same thing as V transpose multiplied by this matrix. But then I can combine these two by taking the transpose of A transpose V. Because when you take the transpose of the product of two matrices, the order flips, which means that this is the same thing as this. And that means that A being self-adjoint really means that A is a symmetric matrix. So that's the definition if you want. A matrix is symmetric if its transpose is equal to itself. Now the spectral theorem says something about the spectrum and the eigenvalues and eigenvectors of a symmetric or self-adjoint operator or transformation. It says, first of all, that any eigenvalue is going to be real. So no complex, no imaginary parts whatsoever. And furthermore, it says that there's a basis, epsilon, of Rn that is simultaneously an eigenbasis for A and is orthonormal. Okay? So first of all, I'm saying that A is diagonalizable. And second of all, the eigenspaces are orthogonal to each other. So maybe I should write it like this more explicitly. What people say is that A is orthogonally similar to a diagonal matrix, or A can be orthogonally diagonalized. Which means that if I were to take these vectors, certainly if I were to put them in a matrix Q as columns, okay, so the columns of the square matrix would be orthonormal, which means that it would be orthogonal. It would be an orthogonal matrix. So this is an orthogonal matrix. And A would be equal. So if I were to use this coordinate change, right? A would be Q d Q inverse. But of course, the beauty of using an orthogonal matrix there to change your coordinates is that the inverse of an orthogonal matrix is its transpose. Okay? So instead of taking this inverse, you can just write it like this. So you can also say that A is orthogonally similar to a diagonal matrix. Okay. Now, I'm not saying that the eigenvalues of A are distinct. I'm just saying that they are real. Maybe you have repeated eigenvalues. Okay. So let's look at examples. Two, 1, 1, 1. Okay. This is a symmetric matrix because if I were to take the transpose, I get back the same matrix. Now, the spectral theorem tells me that without doing anything, that the eigenvalues are going to be real. And that A is diagonalizable. And further, that the eigenspaces are going to be orthogonal to each other. Okay? So that's the prediction based on the spectral theorem. So let's go through the motions and see. Looking at the characteristic equation, so I have lambda here. Minus 2, minus 1, minus 1, minus 1, like this. I want this determinant to be 0. So this is lambda minus 2 times lambda minus 1 minus 1. Now this is lambda squared minus 3 lambda plus 1. Okay. Let's say we use the quadratic formula. The quadratic formula would say that the roots of this equation is minus b plus or minus b squared minus 4ac is root 5 divided by 2. Okay, you see, these are real numbers. I have distinct real eigenvalues. Okay, as was predicted by the spectral theorem. And since A has distinct real eigenvalues, I know that it is diagonalizable. But really, the second item is saying something further. It says that it is orthogonally diagonalizable, which means that the eigenspaces associated to these two eigenvalues are going to be orthogonal to each other. So let's find out eigenvectors as well and see that this is indeed true. So let's say that lambda 1 is the one with the plus. Okay, now I need to find an eigenvector for this. Putting this in the diagonal, and then subtracting the entries of A, I have this, minus 1, minus 1. So this is my matrix. I want to find a vector in the null space of this matrix. Let's do this. So this number is 3 plus root 5 divided by 2 minus 4 divided by 2, which is the same thing as minus 1 plus root 5 divided by 2. So really the first equation, if I were to set xy here equals 0, 0, would tell me that x times this minus y equals 0. So maybe I should write it. Minus 1 plus root 5 divided by 2 times x minus y equals 0. So an eigenvector for this would be, if I were to plug in x equals 1, y would be this number. Okay. So this is an eigenvector for this eigenvalue, for A. Let's verify this while we're at it. I'm just going to do the verification over here. So the idea is that if I were to take this vector and multiply it by A from the left, I should get back some multiple of this. And the multiple, that scalar should be that number really. So 2, 1, 1, 1 multiplied by that vector gives me this. So 2 plus this number in the first entry. And in the second entry, 1 plus the same number. Okay. So in the first entry, I have 4 plus this. So that gives you 3 plus root 5 divided by 2. And here it gives you 1 plus root 5 divided by 2. Okay. So now I want to factor out this number, right? Because that's over there. So if I were to factor that number out, I would get this here. In the first entry, I would get 1. In the second entry, I would get this divided by this. So this is so 2 over 3 plus root 5 times 1 plus root 5 divided by 2. And so this product we need to compute. Let me do it somewhere else. So that's 1 plus root 5 divided by 3 plus root 5. I want that number, right? So this is the second entry of this vector. I want that to be equal to this number. Like this. Okay, send this to the other side, send this to the other side. So this is 2 times 1 plus root 5. Is this equal to 3 plus root 5 times minus 1 plus root 5? Here I have 2 plus 2 root 5, and here I have minus 3 plus 3 root 5, minus 1 root 5 is plus 2 root 5, and then plus 5. which is the same thing as this, of course. Okay, so it does work. We checked that this calculation was indeed correct. So that is one eigenvalue, and that is an eigenvector for it. Of course, we're not done. We need to compute an eigenvector for the other guy, for the second eigenvalue, which is the same expression, except that instead of a plus root 5, I have a minus root 5. Now, assuming that the spectral theorem is correct, at this stage, I actually don't need to compute a lot of things, right? So I can just look at some vector and look at the orthogonal projection of that vector onto this eigenspace. The complement, what is left, is going to be an eigenvector. Because I know that the eigenvalues, based on the spectral theorem, the eigenspaces associated to distinct eigenvalues are going to be orthogonal. But we're just going through the motions and computing the things just so that it is, we have more evidence, let's say, as to why this spectral theorem should work. Okay, so the other eigenvalue is lambda 2, and that's going to be 3 minus root 5 divided by 2. And again, I want to come up with an eigenvector for it. Putting this in the diagonal. And then subtracting the entries of A, I get this time. Now this is my new matrix, and I want to find a vector in the null space of it. Okay. Just as I did over here, I can just consolidate that expression over here. So this is 3 minus root 5 divided by 4 by 2 minus 4 divided by 2, which is minus 1 minus root 5 divided by 2. So the first row is really telling me that this times x, so minus, well, let me just leave it like this, divided by 2 times x minus y equals 0. Okay? So, for instance, I can then use this for v2. If I were to plug in x equals 1, then y would be this number. Let me not go through the verification that this is indeed a correct calculation. It's very similar. In any event, we were able to find one eigenvector and the other one eigenvector, another eigenvector over there. Now let's look at the angle, or the inner product of v1 and v2. If we were to compute the inner product, let me do it over there. I guess we don't need this anymore. So v1 was 1, and then this other number. And then v2 is there. Okay, so now I need to compute this inner product. This gives me 1 plus the product of these two. Minus 1 plus root 5 times minus 1 minus root 5 divided by 4. Okay? So this is of the form a plus b times a minus b. So this numerator is going to be a squared minus b squared. So this is 1 plus a squared is 1 minus b squared is 5 divided by 4. Okay? So 1 minus 5 is minus 4. So this is minus 1. So they are orthogonal. Okay? So eigenspaces corresponding to distinct eigenvalues are not only linearly independent, but in fact they are orthogonal. They are at 90 degrees when you were to draw these, on the plane. Okay? Which means that if I were to use as my coordinate change matrix, that matrix whose columns are these vectors up to normalization, then things would be very nice. Because at this stage, I don't know the norms of these. But you see, this is sort of a somewhat confusing terminology. We call the matrix Q orthogonal if its columns or rows are orthonormal. So I would need to orthonormalize or normalize these vectors to come up with epsilon vectors, epsilon basis vectors. Let me not go through that. It is a rather straightforward calculation, but this is the idea. Okay? Now, any questions about this? As you can imagine, this is very powerful. You see, I didn't need to go through all this calculation with root 5 and stuff. At least for sort of broader understanding, of course, if you're actually interested in the exact values of the eigenvalues, you need to compute things. But at the very least, once you have a symmetric matrix, you know that its eigenvalues are going to be real, and it's going to be diagonalizable via an orthonormal change of basis matrix. Okay. So this is that. Let's do another example. 3 by 3 this time. 6 minus 2 minus 1 minus 2 6 minus 1 1 minus 1 5. Sorry, minus 1. Okay, so this is my matrix. It's 3 by 3. Now, immediately I realize that this is a symmetric matrix because I don't look at the diagonals, but I look at the off-diagonal elements, and this has to match up with this, this with this, this with this. So I know by the spectral theorem that the eigenvalues are going to be real. I know that this is diagonalizable by an orthogonal matrix. By spectral theorem, already know that for some orthogonal matrix Q, and for some diagonal D, A equals QD Q transpose, the columns of Q are going to be the eigenbasis vectors, and the entries of the diagonal are going to be the eigenvalues. Okay. Now at this stage, if you want to compute things, like if you want to figure out eigenvalues, you need to compute things. But already you know so much. So let's try to compute eigenvalues as well. Or maybe let me not do it. It turns out when you go through the motions, you set up the characteristic equation and everything. It turns out that the eigenvalues are 3, 6, and 8. Okay, so they're real. So some calculations gives you this, and that therefore the diagonal matrix is like this. Okay. You can also think of the spectral theorem as giving you some sort of heuristic, right? Because if you start with a symmetric matrix, you know that when you're trying to compute eigenvalues, you're going to end up with real numbers. So at some stage, if you start seeing complex numbers, that means that you made an error somewhere. So this is that. Any questions about this? I don't think I'm going to go through the proof of the spectral theorem. Just slightly advanced, but perhaps if you have time later, we can discuss it a little bit. Now, based on this idea of the spectral decomposition, based on this idea of the spectral theorem, there's an associated spectral decomposition. Okay. Okay. This essentially says the following, that if you have a symmetric matrix, so that the spectral theorem applies, your matrix is a linear combination of orthogonal projections onto one-dimensional spaces. Okay, let me write it. Any symmetric matrix is a linear combination of orthogonal projections onto one-dimensional subspaces. Okay? Let's first understand this idea of orthogonal projection onto a one-dimensional subspace. Of course, we know what this is, but I would like to think of it as a matrix so that I can split my matrix A into such matrices. So what is the matrix of orthogonal projection onto a one-dimensional subspace? Well, what is this? So from last week, let's say that I have a vector u. And let's say that to start with, it is normal, right? So let's say that I normalize it, and let's say that S is the span of u. So it is a one-dimensional, or let me say L for line. This is a span of u. I want to figure out the matrix that corresponds to proj sub S of V, or proj sub S. Well, the formula for this. Oh, yeah, sorry. What is this? This is V against U divided by U norm squared. But I said that I already normalized my vector, so it has norm 1 times U. Okay, now what is this? So the idea is this here. I want to manipulate this expression in such a way that eventually I can take out V so that I can talk about this guy. So what is this? This is so this is a number, this is a vector. Maybe I can write it even explicitly. So this would be V against U times U1, U2, dot, 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 UN. This is a number, so I can put it into the vector. Give me a second. I don't know if this is the fastest way of saying this. Just make it confusing. Let's do this. Give me a second. So if I were to do this, that would be the U norm, which would be just 1. So it really should be the other way around. This should be the matrix that I should get eventually. So that expression should be the same thing as this. Oh, okay. I got it now. So this is the same thing as U against V times U Okay, but this is a number, so I can put it on the other side. Okay, but then this is nothing but U transpose U, V. Okay, so this projection operator really is given by this matrix. Maybe I should just write proj sub U, because that was the notation that we used last week as well. So this times V equals U transpose times V. Which means that you see this matrix corresponds to projection onto the space spanned by U. Of course, we did the same idea yesterday when we were trying to extract this QR factorization from the Gram-Schmidt process. We had a Q matrix whose columns were orthonormal. In this case, you can imagine Q to be that matrix that has one orthonormal column, right? So this U is that Q from yesterday, really. And this corresponds to the projection operator. Now note that if U is in Rn, I'm representing it by an n by 1 matrix, which means that the dimensions of this are n, 1, n. So this is an n by n matrix. So this is a linear transformation from Rn to Rn. And since it is onto the one-dimensional space spanned by U, its rank is 1. Its column space has to be one-dimensional. So this is a rank 1 operator. And so for instance, if I were to start with a diagonal matrix, then I can write it like this. So let's start with the diagonal matrix here, 3, 6, 9, 3, 6, 8. Certainly I can write it like so. Okay. But then this really is 1, 0, 0. It really is the projection operator onto 1, 0, 0. Okay. So let's try it here. Proj 1, 0, 0 would be based on that expression over there. 1, 0, 0, 1, 0, 0. But of course, if I do this multiplication, I'm going to get a 3 by 3 matrix. And in the first row, I'm going to see this, and the second and third rows are going to be 0. You see, this matrix really is the projection operator onto 1, 0, 0. And likewise, this is the projection operator onto 0, 1, 0. And this is the projection operator. Onto 0, 0, 1. Okay. So this diagonal matrix, which is symmetric, as you can see, I was able to write as a linear combination of projection operators onto one-dimensional subspaces, and of course the coefficients are the eigenvalues. Okay. Spectral decomposition says the same thing holds in general. It says this. If A is symmetric, then by the spectral theorem, I know that I have n eigenvalues, possibly repeating. And there's a basis for our n that is both an eigenbasis for A and orthonormal. And epsilon and let me just say ONEB, orthonormal eigenbasis, then A really can be thought of as lambda 1 multiplied by projection operator onto epsilon 1 plus lambda 2 times projection operator onto epsilon 2, and so on, all the way up to lambda n proj sub epsilon n. Okay, and if you want, you can abbreviate this like this as well. Okay. Some people do take the statement of the spectral theorem as this, as that you can write any symmetric matrix as a linear combination of rank 1 matrices. Okay. Any questions about this?
So like so we're swapping out like the normal standard basis that we're using there for like the eigenbasis?
Yes. Yeah. Exactly. Yeah. So maybe we can go through the calculation a little bit. Let's try to understand why this will be true. Certainly it is true in the case of diagonal matrices. So if I'm in this situation, and if I put epsilon 1 to epsilon n as the columns of a matrix Q, now I have this orthogonal matrix. And I have the diagonal matrix, which is lambda 1, lambda 2, dot, 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 lambda n. And the spectral theorem tells me that A equals Q d Q transpose. Okay. So Let me see. Okay, let's write it out. Now I'm expanding. Actually, let's do this for n equals 3 so that we can write it faster. Of course, the idea holds in general, but my Q, my diagonal matrix is here. And then I have Q transpose, which means that I'm going to see the eigenbasis vectors as row vectors. Okay. Now, this is going to be a 3 by 3 matrix whose columns are lambda I times epsilon I, right? Because I'm just multiplying things. So here, so lambda 1 times epsilon 1, lambda 2 times epsilon 2, and then lambda 3 times epsilon 3. Like this. And then I have this other matrix. Now you see, this by this, really I should write as lambda 1 times epsilon 1 times epsilon 1 transpose, because I'm thinking of it as a row vector. So this really turns into this. And based on what we discussed, these are the projection operators, as you can see. So you see, so when you do this multiplication, because epsilon i's are orthonormal, you get to split this way. If it were the case that epsilon 2, for instance, is not orthogonal to epsilon 1, you would need to have sort of some mixed term as well. But in this case, all those mixed terms are going to vanish. And you end up with this expression, which is the expression analogous to this splitting over there. Okay? Questions? Okay, that's it for today. We're going to continue tomorrow with sort of like a more geometric interpretation of all this stuff. Thank you. Okay, let's start. Good morning. So today I want to start talking about something related to this whole theory, which is quadratic forms. But before going into that, I wanted to go over the spectral theorem again and do a correction. I think I made I did an error yesterday, so I wanted to correct that. So let's go over the statement, and this is the real version. So for complex, so when you sort of start talking about matrices with complex entries, the statement is analogous but slightly more sophisticated. So this is the real spectral theorem. If I have a square matrix A that is symmetric, which means that its transpose is equal to itself, then the spectral theorem says a bunch of things. They're all essentially equivalent statements, but depending on the problem that you're trying to handle, the statement that you want to use turns out to be different. So one of them is that each eigenvalue of A is real, which means that when I take my matrix A and plot its spectrum, right? We can do that. A priori, it can be your eigenvalues can be complex numbers. Yeah. So let's say that you're trying to plot it. But whenever you start with a symmetric matrix, the spectral theorem says that you're always going to have values here on the real axis. OK? So that's good. I'm not saying that these are going to be distinct. Maybe they repeat. OK? That's the first item. Second item is that there's a basis, epsilon, of, this is epsilon i's are all vectors in Rn that is simultaneously orthonormal. So it's an orthonormal basis. Each have length 1, and they are orthogonal to each other. And simultaneously, this is an eigenbasis for A. So, and here, I mean, if I apply A to epsilon I get lambda I times epsilon I. Epsilon I, yeah. So let me write it here. So that's what this means. And in particular, different eigenspaces are orthogonal to each other. This is the second item. Third item is a factorization. So the fact that you have an eigenbasis for your space means that your matrix is diagonalizable. The fact that on top of epsilon being an eigenbasis, it's an orthonormal basis means that you can orthogonally diagonalize. Meaning that this change of coordinates matrix Q, which is the matrix that you obtain by putting your basis elements as columns, is not only invertible, in fact it is orthogonal. So you have this. And so for a general diagonalizable matrix, this expression was Q d Q inverse. But for orthogonal matrices, Q transpose is the same thing as Q inverse. And it is less scary to think about it in a sense. Because when you're trying to compute the inverse of a matrix, it's a chore, essentially. But if your matrix is orthogonal, you know that the inverse is the transpose. So it's much simpler to invert an orthogonal matrix. The fourth item in the spectral theorem is the so-called spectral decomposition, which says that A is a linear combination of rank 1 orthogonal projections. So if this is the projection operator onto the span of the kth basis vector, so let's say this is onto a one-dimensional space, certainly I can take this linear combination as vectors in this matrix space, if you want. And this basically comes from this expression, okay? And so when you write down this orthogonal projection onto the span of epsilon k, it is nothing but this matrix. Now note that epsilon k is supposed to be an n by 1 matrix. So this is n by 1 by n, so it is n by n. So this is an n by n matrix, really. Now, the error that I made yesterday was here. I said something. When I switched from here to there, I said something, and I don't think that was correct. So in this factorization, we have epsilon i's as columns, lambdas in the diagonal, and then epsilon i's as rows. And then I said, oh, when I'm doing this multiplication, because epsilon I is orthogonal to epsilon j, I'm just going to have terms of this form. That is not quite correct, okay? And here's the correction. For any two matrices A and B that I can multiply so that the column dimension of A matches with the row dimension of B, so that AB makes sense, I have indeed this expression. In particular, if somehow you can you can consolidate this entries in the diagonal into either one of these, you get back from here to there, or rather from here to there. So this statement is true. typically when we're multiplying matrices, recall that we split the left one into rows and the right one into columns. When you split it that way, you get every single entry of the product. But you can split it the other way around, and you can split the left one into columns and the right one into rows. Then your matrix, your product matrix AB, would be a linear combination of m by p matrices. This is essentially what I'm using here. And so I thought it would be a good idea to go through this idea. And just so that we don't write too many matrices, I'm going to use some abbreviated notation and some essentially for loops. And here's some definition. Kronecker delta is sort of like a very common symbol. It's of course analogous to this Dirac signal, unit impulse signal in the context of signal processing. So this is just this symbol. Delta ij is 1 if the indices I and j are the same, and 0 otherwise. Okay? And so using this, I can write down the standard basis of any matrix space, really. And so let's look at the space of m by n matrices. That's a linear space. It's supposed to have a basis. And so I'm going to define e to the rs. R is going to run from 1 to m, and s is going to run from 1 to n. You see, using the Kronecker delta, it just allows me to write things very fast. I can define what is the ijth entry of the ERS matrix. It's just this product, which means that this ERS matrix has 1 only in the RS entry and 0 otherwise. Well, if that is the case, certainly I can write any matrix as a linear combination of ERSs, right? Because, so 2, 3, 1, 0, minus 1, 4, for instance. Well, this is nothing but 2 times this. And then 3 times this, and then 1 times the third guy, and then 0 times the fourth guy, I don't need to write it, plus or minus 1 times 0, 0, 0, 0, 1, 0, and then plus 4 times 0, 0, 0, 0, 0, 1. Now this is E11, and so on. That's the idea. So this is E11. This is E12. This is E13. I skip E21. That would correspond to this entry. This is E22. And this is E23. So really, this matrix can be written as this. 2 times E11 plus 3 times E12 plus 1 time E13 minus E22 plus 4 E23. These are all matrices, and I can think of them as transformations, but matrices are elements in a vector space, which is a space of matrices, and I can think of them as matrices as vectors as well, which means that I can, write linear combinations and so on. So if you were to apply the same idea to this, well, all I'm saying is that A is that matrix whose ijth entry is this particular entry. Okay. So now let's try to verify this. You can, of course, try writing everything explicitly, A11, A2, A12, and so on, but it just takes a long time. It's much easier to automate the index counting and everything. So really, to verify this, I'm going to start from this side, okay, and then go back, because it's much easier to see that indeed the sum of matrices of this form end up being the same thing as AB. So let's put here a star. I want to verify that this is indeed the case, that I can split AB, the product, as a linear combination of the products of the kth, or sorry, a linear combination of the products of the kth column of the left one and the kth row of the right one. So, and let me not worry about the bounds of the indices. I'm just going to write the name of the index. So, oh, sorry, it's the other way around. Okay, now this is matrix multiplication, and I can write it like this. Yeah, let's write it like this. Let's write this piece explicitly, okay? So this is going to be A1k, A2k, dot, 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 A nk, oh, sorry, mk. These are the entries of this guy. And the entries of this guy is going to be this. B k1, B k2, dot, 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 BKP. I just took the kth column of A and the kth row of B. So now I get to multiply this. Ultimately, I'm going to end up with an M by P matrix. Okay. So this is A1k, BK1, A1k, BK2, and so on. A1k, BKP. Right, so to get the first row of this product, all I need to do is to take this number and multiply every single entry here. That's going to be my first row. Second row is similar. Now I get to take this number and multiply this row. And finally, I'm going to take this number, multiply it by that row, and that's going to be my final row. So now, finally, I get this. A mk bk1, A mk bk2, all the way up to A mk bkp. And again, I'm taking the sum over all k's. Now let me compress this expression by using this linear combination using the standard basis matrices. I thought it would be a good sort of reminder of matrix multiplication and everything too, as we're sort of wrapping up this class. So how can I write this? So this is going to be a linear combination over all of all eij's, and here I need to put the ijth entry. Okay. So maybe I can write it there actually. So the outer sum is going to stay. There is an outer sum over k, but then I have the sum over I and j. And here I should have e to the ij. That's my matrix. In the ijth entry, I'm going to see a ik b kj. So this expression is the same thing as this expression. Okay. Now the next stage is sort of like changing the order of integration. So you can imagine these sums as discrete integrals, and you get to change the integrals. So I'm going to write it instead like this. Okay? And of course, this guy doesn't depend on k, which means that I can do this iterated integration if you want. But this is nothing but the ijth entry of a times b.
When you say discrete interval, do you mean like Riemann stuff?
No, it's just, I'm just imagining that, yes, essentially, yes.
I mean, kind of. I guess that is kind of the case. But
Yes, that's what I'm saying. Yeah. So this is the ijth entry of AB, but then this linear combination really is nothing but AB itself. Okay? I mean, I am adding terms over some domain, so that's integration. So this verifies that this formula holds. And what I'm saying is that if you apply the same thing over here, you get from the QD Q transpose formula this factorization. Let's do that super fast as well. So 4 from 3 in the spectral theorem. So 4 from 3 in the spectral theorem. So I know that A is equal to Q dQ to transpose. And when I expand these matrices, I see this. Okay. Now what you can do is you can take this product. It's rather straightforward to see this, that this product is really that matrix whose columns are lambda I, epsilon I. Because this you can imagine as, so if I were taking a matrix and multiplying that matrix by this matrix from the left, that would correspond to scaling the rows. Well, if you take this matrix and multiply it from the right, that corresponds to scaling the columns. This is an elementary column operation if you want. And this is exactly the paradigm that we discussed over here. This is nothing but the sum over the products of the columns against rows. That is nothing but this, of course. See? So I just wanted to rectify this. The error that I made was a statement that when you're switching, so the error that I made yesterday was that when you're switching from here to there and then from here to there, what's really happening is that you also have mixed terms, E, I, E, J here, but they're orthogonal, so they're going to give you 0. That is not true, okay? That is false, in fact. I made a mistake there, so I wanted to correct it. This spectral decomposition is correct, of course. Any questions about this? Just to verify that this EI, EJ products don't vanish, when you do this outer product, you can think of it like this. In 2 dimensions, right, I can take the standard basis. So let's say that beta 1 is 1, 0, and beta 2 is 0, 1. Certainly this is an orthonormal basis. of R2. But when I take these outer products, I'm not going to get 0 matrices, even when I take the mixed versions. Or maybe I should do it like this. Now, what are these? Okay, all of these are going to give you 2 by 2 matrices. This is going to give you 1, 0, 0, 0. This is going to give you 0, 1, 0, 0. This is going to give you 0, 0, 1, 0. This is going to give you 0, 0, 0, 1. Okay? Incidentally, these are the basis matrices that I wrote over there. So this is E11 and so on. Okay? Any questions about this mumbo jumbo? It's not significant, of course, but ultimately, index management is an important thing to be able to do. So, yes.
So the upper subscripts.
Yes.
Where does that come from? How does that define?
I'm saying R and S are 2 indices that vary. So R varies between 1 and m, and S varies between 1 and n. So just like here, I have 1 and 2. In the case of a space of matrices, instead of using 1 index, it's probably better to use 2 indices, is what I'm saying.
But what's the significance of the upper subscripts as opposed to the
Yeah, so
superscripts instead of
yeah, so I see. So for any given RS superscript, that gives you 1 matrix. For any matrix, when I write the subscripts, I mean that entry.
the elements of
Yes. So this matrix I call E11. This matrix is that. But E11, 2, 2, for instance, is the 2, 2 entry of E11, which is 0. Okay? So this is E12. It's just a way of iterating these basis elements. Okay? Yeah. Yeah, I mean you can do things. So here's a nice exercise. If you want to get really comfortable with this. Compute this product and then compute the bracket. Right, because E11 times itself, for instance, if I were to choose PQ this, the same as RS, this is E11 squared, but E11 is nothing but a projection operator, which means that its square should be itself. But if I were to take something else, E11 against E12, they are both projection operators. They project onto different spaces. They should give you 0, for instance. You can verify that this is true, even if you have no idea that these EIJs are projection operators. Just like follow the algebra, and it's going to produce for you these relations. Okay. This is not a major thing, of course, but if you take a more advanced class in linear algebra where computations are important and flops and everything are important, these become indispensable tools. Because ultimately you end up needing to sort of write things in a concise manner. But for this class, most things are rather straightforward, so we don't really need this index management aspect of linear algebra. Okay, so I want to talk about this next thing, which is quadratic forms. Okay, let me go over there. How many of you are comfortable with multivariable polynomials? Okay, kind of, yeah. So a quadratic form is a polynomial, possibly multivariable, typically multivariable, each of whose terms are of degree 2. So let me be explicit. So So a polynomial, for instance, I can think of this, p of xy, right? So x plus y plus x squared plus xy plus x cubed y 7. That's a polynomial of 2 variables, and I can put numbers if I wanted. Minus 2 here, 5 here, and so on. Okay? Now, if you have a 1 variable in your polynomial, it's typically good to sort of like start from the lowest degree and slowly write all the way to the highest degree. If you have 2 degrees, if you have 2 variables, you look at the degree of each of these terms. So I would say, for instance, that this is a degree 1 term. This is also a degree 1 term. This is a degree 2 term. And this too is a degree 2 term. Okay? And then this is a degree 10 term, and this is a degree 0 term. So these two, degree 2, this, degree 10, and this, 0 degree. So the systematic way of writing a polynomial, let's say in 2 variables, would be like this. I would start with 0 degree, that's just a number. And then degree 1 would have an x term and a y term. Degree 2 term would have an x squared term, xy term, y squared term, and so on. So P00, here I really mean by this the coefficient next to x to the 0 times y to the 0. And then P10 is going to be next to x. And then P01 is going to be next to y, and so on. Okay? So, and then order 3 terms would start with 3, 0, and I would have x cubed. And then I would have x squared y, and then I would have xy squared, and I would have y cubed. That would be the degree 3 terms. And then I would have degree 4 terms and so on, however many degrees I have in my polynomial. Okay? So really you want to think of this as little blocks like this. And a polynomial is called for any integer, let's say s, a polynomial called is s-homogeneous if it satisfies a certain scaling property. Now, I really need to talk about I really need to think about multivariable polynomials. So when I'm thinking of a polynomial, I'm really thinking of a function on Rn. Here it was R2. I had 2 variables. Now I have n variables. Maybe I should write it like this. Is s-homogeneous for s an integer if p of cv, scalar multiplication of a vector in Rn, is not exactly PV, or not really C times PV, but C to the S PV. Okay. A quadratic form on Rn is going to be a 2 homogeneous polynomial. Two homogeneous. Now let's look at this. If I were to just ignore everything but the 0th degree term of this particular polynomial, what would its homogeneity degree be? So that SP. So I'm plugging in xy. Maybe I should write it like this. So here's an example. Let's just stick to 2 homogeneous polynomials. So let's say that I have a 3-variate polynomial, and let's say that it is like this. It is x squared plus xy plus 2yz. Okay? And let's say minus z squared. Now you see each of these terms have degree 2. And if I were to scale my vector by some constant, now from here I'm going to get c squared times x squared. From here I'm going to get cx times cy, so that's going to be c squared again. You see? If you keep going like this, you're going to realize that p of cx, cy, and cz equals c squared times this. And if you had some other degrees, let's look at x to the 5, y to the 7, for instance. Now, what is the homogeneity degree of this?
That's a 7, right?
7?
That's a 7.
Yeah, that's a 7, yes.
What is that, 12?
Yes, right? So this is a degree 12 polynomial, and its homogeneity degree is also 12. So when I say Q is a quadratic form, I really mean that it's a polynomial, all of whose components are degree 2 monomials. It's hard to sort of write it in a nice way, but in 2 dimensions we can certainly write every single one, or the general formula, in a fairly straightforward fashion. In fact, let's start with 1 dimension, okay? On 1 dimension, we can still talk about quadratic forms. So I want this to be a quadratic form, which means that when I scale x by c, the outcome should be scaled by c squared. Okay? The only way this can happen is if it is like this. Okay? So in dimension 1, any quadratic form is a constant multiple of x squared, because that's the only degree 2 thing I can come up with. In dimension 2, things are slightly more complicated. Now I can use mixed terms as well. I have x squared, y squared, and xy, and these are the only 3 terms. A, B, C can be any 3 numbers. Not the same C as that C, of course. This is the coefficient of the polynomial. In dimension 3, it gets even more complicated. I need to run through every single degree 3 term. So x cubed, x squared y, and so on. So A, B, C, D. Okay? And this should be C cubed. Oh, no, that's not correct. Sorry. This is not the end. It takes a while. Okay. X cubed, x squared y, x y squared, y cubed. Let me write it like this: x squared y, x squared z, and then okay, I'm going to cheat because it's not that important writing these down explicitly. Ultimately, you end up with z cubed, of course. You write down all of these terms, and you have some numbers that you need to figure out. Okay. Now, the idea is that using the spectral theorem, and the reason why I'm talking about this, is that using the spectral theorem, you can really simplify these expressions. What you want to do is, oh, that's wrong. What you want to do is you want to get rid of these mixed terms. You want to have x squared, y squared, z squared, whatever. You don't want to have mixed channels. And indeed, the standard inner product is of that form. And so the standard inner product on Rn is a quadratic form. It gives you a quadratic form. And likewise, the Minkowski inner product gives you another quadratic form, for instance. Here are more examples. So Q of V, let me write. V against V is a quadratic form. on Rn, and so is the Minkowski form. So let me write it like this. Q of v, which is v against v, according to Minkowski, is a quadratic form on R4. This was the Minkowski form, Minkowski inner product. Okay. Now, based on this, at least this first example, this actually gives us a way to apply the spectral theorem to this situation. Because any quadratic form really can be packaged into a matrix product. So for any quadratic form on Rn, there is a unique symmetric matrix of dimensions n by n. Such that Q of v really is v against m of v. How come? Well, let's just look at that situation. Let me start with an arbitrary matrix like that. So xy, a, b, b, c, right? Because I'm saying that m has to be symmetric against xy. Now I need to take this inner product. When I take it, I get this. Let's do it step by step. Ax plus by in the first row, and in the second row I have bx plus cy. And then when you take this inner product, you get this. Ax squared plus bxy plus another bxy, which means that I have 2bxy, and I have plus cy squared. You see, it's not exactly that formula, because in the middle I have not 2b, I have b there. But if you started with this, certainly you could sort of halve that middle term and put it in the diagonal. And that would give you the matrix, the symmetric matrix corresponding to the quadratic form. So for instance, in this case, the unique symmetric matrix is the identity matrix, of course. Okay, so in this case, the unique symmetric matrix is the matrix that is 4 by 4 and diagonal. And one of the diagonal entries is -1, that corresponds to time, and the other 3 are plus. And certainly this matrix is symmetric. Okay? Any other quadratic form is of this form, is what that is saying. Well, if any quadratic form is pretty much a symmetric matrix used a certain way, well, you can apply the spectral theorem to it and say something about it. Okay? I have a couple minutes. And so this is the geometric version of the spectral theorem. It's what's called the principal axis theorem. Any quadratic form, let's say it this way, is given by a diagonal matrix up to an orthogonal coordinate change. And here's what I mean by this. Let's say that my matrix is, so the matrix that defines a quadratic form is A. So this really is this. But A is symmetric which means that by the spectral theorem, I can decompose it into QD, Q transpose. And then I can take this factor to the other side as Q transpose. You see now this is, if I were to take this as the input, that's my coordinate change. Now this is the same thing as W against dW. This is yet another quadratic form. That's what I mean. And this Q, or Q transpose, is this coordinate change. So if I have here Q, and I have Q hat, so Q hat of Q transpose V is the same thing as QV. So instead of going from here to there, which corresponds to this, what you can do is you can first go here using Q transpose and use this. Or in other words, you have this diagram. Okay? So this Q is your coordinate change matrix. And certainly its columns, based on the spectral theorem, are this eigenbasis that is orthonormal for A. Those columns are called the principal axes of Q. So let me write a T here too. And what is more, Q hat really is of this form, right? Because it's given by this diagonal matrix. Let me write it here, and that will be the last thing I will write. Lambda I Wi squared. So you would be killing any mixed terms, you see. You would have only squares of the variables. We're going to discuss this a little bit more on Friday. And then one final thing that we should really cover is this singular value theorem. Probably I'm not going to talk about something called the constraint optimization of quadratic forms, as we already talked about some optimization problems. But once we cover the singular value decomposition, we'll be done mostly for the midterm topics. Okay. Thank you. Okay, let's start. Good morning. So today we're going to cover the final major topic of this class, singular value decomposition. And after that, next week, we're going to discuss some dynamical systems, fun stuff. And of course, we have the midterm on Friday next week. And then the week after, finally, we'll finish the class with what we started, which was this PageRank algorithm. Everything is going to basically come together, I hope, and that will be the end of it. Before we start talking about the singular values, I wanted to say a couple more words about these quadratic forms. And even before that, I wanted to make a correction. One of your colleagues out in the last class mentioned this, that when I was writing the general form of a quadratic form on 3 dimensions, on R3, I confused what I was writing down. So it should be like this, right? So you should only have degree 2 terms, and you should have basically every single combination. And if you want, as I was thinking as to how to never make this mistake ever again, I realized you can use these tetrominoes that we use in the context of determinants to sort of like list everything. Okay, so these terms are of this form, because you see it's the same type, you have 2 of them, but here you have mixed. And if you had sort of more general polynomials, you can imagine how every single piece could be attributed to one of these tetrominoes. And essentially the idea of using the spectral theorem in the context of the quadratic forms, which is this principal axis theorem, as you know, is about looking at a polynomial like this and getting rid of these flat tetromino terms. You want to get rid of these terms up to a change of coordinates, and all you want to end up with are these, which is possible because any quadratic form is defined by a matrix that is symmetric. So let me remind that. Any quadratic form on Rn is defined or is determined by a unique symmetric A, which is an n by n matrix. And how do you do this determination? It is merely this. So Q of V is AV against V. So for this guy, how would I write the symmetric matrix corresponding to it? Well, I would say this. Okay, so you see one factor of x, let's say, is going to come from this, and the other one is going to come from this. So recall this was like this. So V transpose A V. So I'm taking the same vector and I'm interpreting it both as a column vector and a row vector, and I'm doing this multiplication, and that gives you a second order terms. So how would I write this? So these terms are going to go to the diagonal, and then xy term is going to be the same thing as the yx term when I'm looking at the matrix here. So this I can write like this. This is the xyz vector that is written as a row vector, and then I'm going to have a 3 by 3 matrix, and then I'm going to have xyz like this. And so here A, B, C I put, and these are coming from the diagonals, and here are the mixed terms. But because this and this are going to be the same, you see, I'm going to have to put half this. So xz is e over 2 here, e over 2 here, and then f over 2 here, f over 2 here. And that's a symmetric matrix, which means that you can apply the spectral theorem to orthogonally diagonalize it, which again is going to be a symmetric matrix, which again, when you switch over to the quadratic form, these terms are going to vanish now. That's the beauty of this. Now let me also say that the typical convention seems to be that instead of using letters here, you put twice d, twice e, twice f, because here you want to have like a nice matrix, essentially. That's, as I understand, is the convention, but you can do it either way, of course. So there's a classification of quadratic forms that is important. You call a quadratic form positive semi-definite if it is non-negative for any v whatsoever, for any input. And it is positive definite if it is positive semi-definite, but also it vanishes, it becomes 0 only when the input vector is 0. And negative semi-definite and negative definite is the same things, but you have the other sign. And if it's none of these, you call it indefinite. So what are examples? Of course, the standard inner product, or rather the quadratic form defined by the standard inner product is positive definite, right? Because the quadratic form defined by the standard inner product is nothing but norm squared. So this is the quadratic form defined by the symmetric matrix. That is the identity matrix, which is also the inner product of a matrix of a vector by itself. V norm squared is positive semi-definite. It satisfies this, but this is stronger, of course. Any positive definite is also positive semi-definite. So I'm just going to write it plus plus. Writing positive definite it takes time. So what's an example, for instance? So if I were to take minus v norm squared, well, that would be negative definite, of course. And then if you were to look at the Minkowski norm, right, the quadratic form defined by the Minkowski inner product, that would be indefinite because it has a negative term. So recall that this was the distance or norm squared in the context of spacetime. And you have a minus sign somewhere, and that gives you indefinite, is plus minus. So all of these are important, different variations. Let me also say that because there's this correspondence between quadratic forms and symmetric matrices, you have the same terminologies applied to symmetric matrices as well. So you might see in the literature, this symmetric matrix is positive definite. That's also a terminology that people use. And what is the definition? A symmetric matrix is, for instance, positive semi-definite if the quadratic form defined by it is positive semi-definite, and so on. So let me say, so this terminology applies to symmetric matrices as well. This taxonomy applies to symmetric matrices also. Let me give one more example. Okay, so how would you generate more examples of positive definite or positive semi-definite matrix quadratic forms? What you can do is this. Let's take the standard quadratic form on Rn. So let me write it like this. Let me have it on Rm, actually. And if I were to take a matrix that is m by n, so that A is a linear transformation from Rn to Rm, well, I can apply this transfer of structure idea that I mentioned, I think, last week. So I can define a quadratic form. Let's call it Q hat on Rn by just saying this. Let me take any vector. Q hat of that vector is going to be Q of A of that vector. So I take an n-dimensional vector W, apply apply A to it. So A is from Rn to Rm. So when I apply A to it, now it's going to be a vector in Rm, which means that I can take the Q quadratic form output of this. So this would be nothing but A of V norm squared. Maybe I should ask this. In order for this to be a quadratic form, there should be a symmetric matrix corresponding to it. What is the symmetric matrix here? Right, so I said over there that any quadratic form is defined like so. In order for Q hat to be a quadratic form, this Q hat too should be of the form V against some matrix times, W against some matrix times W. Okay, this is an important idea. It's a very simple algebraic idea, but it takes a while to get used to being able to do this. Think of it like this. Okay, AV norm squared is the inner product of, AW norm squared is the inner product of AW with itself. Now what is this? This is this transpose times this. And then distributing that transpose into these components, I can send this, the transpose of this, to the other side. Now note that this is a symmetric matrix. This is an, so A is m by n, which means that this is an n by n symmetric matrix. Right? Because A transpose A, transpose, now I need to flip the orders. A transpose times A transpose transpose. But the transpose transpose is the same thing as A, because transpose is an involution. Okay? So it's a symmetric matrix. This is a symmetric matrix that defines this sort of Q hat quadratic form. Okay? Now, so what is the classification of Q hat? Well, it's going to be positive semi-definite. Certainly, Q hat ultimately is the norm squared of something. There's no way that this is negative. But maybe A has some null space. So maybe some of the vectors, even though they are not in, so as W, they're not necessarily 0, but maybe once you apply A to it, it becomes 0, which means that Q hat quadratic output would be 0 for those. So in general, you would say that Q hat would be positive semi-definite. Okay. Um, let me think. Yeah, so let's write this out explicitly then. So let me say it this way. I'm going to write the same thing. Let Q be a quadratic form defined by the symmetric matrix A. So this means that QV equals V against AV. Or if you want, this is the same thing as V transpose AV. Okay. Applying the spectral theorem to A, because spectral theorem says that any symmetric matrix can be orthogonally diagonalized. So up to some orthogonal coordinate change, A is a diagonal matrix. Applying the spectral theorem to A gives an orthogonal Q and a diagonal D such that A equals Q D Q transpose. Well, if this is the case, then I can say that Q of V is the same thing as V against AV, which is the same thing as V against Q D Q inverse V. Inverse or transpose. Sending this factor to the other side, I have this. So now you see this, I'm thinking of this Q as a passive transformation. I'm thinking of it as a coordinate change that is orthogonal. So this is just, it's actually the same matrix, or it's the same vector, but its name is different, I'm imagining. That's a coordinate change. So I'm thinking of this as W, this too as W, so that now I have yet another quadratic form. But you see now you have no mixed terms whatsoever because this guy is diagonal. So let me call this Q hat of W, and Q hat has no mixed terms. Maybe I should write this even more explicitly. So using that Q hat, so Q of V equals Q hat of W, which according to that is W against dW. D is supposed to be a diagonal matrix, and based on the spectral theorem, on the diagonals I should be seeing the eigenvalues of A, right? Maybe they are repeating, but I know that all of the eigenvalues are there.
Repeating, you said?
Yeah, it could be repeating, yes. Because the identity matrix is diagonal. Certainly it is a symmetric matrix. Spectral theorem would give itself. So your eigenvalues could repeat. So let's say that D is like this, lambda 1 to lambda n, and everything else is 0. Well, what is this then? Let me write it explicitly. This is lambda 1 times w1 squared plus lambda 2 times w2 squared, and so on. Now, for instance, if it were the case that all eigenvalues of A are positive, which means that it would mean that all of these lambda i's, all of these coefficients are positive numbers. Well, all of these squares are also positive numbers, no matter what input you put, which means that Q would be positive definite if and only if the corresponding symmetric matrix has all eigenvalues positive. And it would be negative definite if all eigenvalues of A are negative. And it would be indefinite if A has both positive and negative eigenvalues. Okay? So that's sort of a matrix classification of, that's a way of using the spectral theorem to classify quadratic forms. So let me write it here. So the quadratic form is positive definite if all eigenvalues of the corresponding symmetric matrix is positive. I know that because A is a symmetric matrix, by the spectral theorem, all eigenvalues of it are going to be real numbers. I don't know their signs. So classification of the quadratic forms in the context of this positive definite business is about the signatures, the signs of the eigenvalues. Not necessarily the values, but the signs. Q is negative definite if all eigenvalues of A are minus. It is, let me not keep writing this, it's the same idea. It is indefinite if you have positive eigenvalues and negative eigenvalues and so on. Okay, so here's a numerical example. Let's look at the symmetric matrix 2, 1, 1, 1. And I'm considering the quadratic form defined by it. Yes? Spectral theorem.
Because we'd like to learn if it's diagonalizable, because it's a diagonal matrix?
Not necessarily. There are diagonalizable matrices whose eigenvalues, so if a matrix is diagonalizable, all eigenvalues are zero. All eigenvalues are real. But I'm using why am I getting confused about this? Maybe you should ask more. Say more as to what is confusing you.
I remember maybe one of y'all remembers exactly what it was. Like there's like a property where instead of writing like V equals like Q D Q inverse, we can write V equals Q D Q transpose. But there's like a special case where that can happen, and that's the case you're talking about. And that case is where all the eigenvalues are real, and you know all the eigenvalues are real because of something.
Well, yeah, I know that all eigenvalues are real because the matrix is symmetric.
Yep.
Okay, yes. So the spectral theorem tells you that, yes.
Because A is symmetric, not because...
Yes, A is symmetric.
Like the original, not when it's re-represented in the matrix, other matrix transpose.
No, yeah. So A itself, okay. So the spectral theorem, so we have this A, okay, let's read this. I start with a quadratic form. There is a symmetric matrix defined by it, or that it defines. Now, any symmetric matrix, according to the spectral theorem, can be decomposed like this, okay? this is a diagonalization.
Not necessarily because it was written on the board.
Okay. This is a diagonalization of A. It's saying that you can diagonalize A using using an orthogonal matrix, so that Q inverse is Q transpose, and here is the diagonal. And on the diagonal, you see the eigenvalues, of course. Yeah. So the example is let's say that I'm looking at 2, 1, 1, 1. It's a symmetric matrix. It defines a quadratic form uniquely. So what is that quadratic form? All I need to do is to compute this product. Based on what we discussed, this is going to turn into this. 2x squared coming from this plus y squared. And then I have 2xy. Okay, this is a quadratic form. Okay, now so this is a symmetric matrix. We've gone through the motions with this, and I think we computed the eigenvalues to be 3 plus or minus root 5. We did this the other day. So A is equal to Q d Q transpose for some orthogonal matrix Q, such that on the diagonal I have 3 plus root 5 divided by 2 and 3 minus root 5 divided by 2. Okay? Now, I don't want to use xy because I need this coordinate change. But insofar as I can do this coordinate change and switch over to w, which is q transpose xy, whatever that is. So let's say uv is q transpose xy. Then if I do this coordinate change, this quadratic form turns into this number times u squared plus this other number times b squared. That's what this whole thing is telling you. Now, 5 is less than 9, which means that its square root is less than 3, which means that this is a positive number. This too is a positive number. Both of these are positive, which means that this guy is positive definite. Okay? That's how you do it. Let me also mention why this would be useful. In single variable calculus, we learned that the derivative is supposed to be, so when the derivative is 0, that tells you when you have critical points. And then you have the second derivative test for concavity. Is it a minimum or a maximum, at least locally? Now, if you go to higher dimensions, there too is a version of differentiation in higher dimensions. It's about tangent planes, for instance, in 2 dimensions. And again, you can look at the critical points as when the derivative is 0. But then you want to say, oh, what, for a multivariable function, is this critical point a maximum or a minimum? So you need something like a second derivative test. And it turns out that in higher dimensions too, in multivariable calculus, there too is a test for this. And it turns out that given any function that is differentiable and so on, there is a quadratic form that you can associate to it. It's called the Hessian. And based on whether or not that quadratic form, the Hessian is positive definite, positive semi-definite, and so on, you can deduce if that critical point that you're looking at is whether it is a minimum or a maximum or whatever. Okay? So this is why this is an important thing. Yeah.
We're talking about quadratics, but we said earlier that if you can diagonalize a matrix, it becomes pretty easy in a relative sense to take the powers of it.
Yes.
And so I'm just wondering, can you use this kind responses, even if it's not a quadratic? Because I guess it sounds like if it's not a quadratic, you could just represent it in a way that makes it, like you could represent, like you basically factor out a quadratic, diagonalize the quadratic like in this way, and take powers of that quadratic form, and then maybe you'd get back to that whatever n power.
So you start with, for instance, a general polynomial is what you have. Okay. If you had degree 3, then you can still represent it, but it's not going to be a power of a matrix. It's going to be, so a matrix is a two-dimensional array of numbers. So for degree 3, I would assume that you would use a three-dimensional array of numbers. These are called tensors. So matrix multiplication is something like that, actually. So computer scientists like drawing these like three-dimensional matrices and so on to represent these tensors. You don't really take the powers of a certain matrix. You need to have something like this now. You need to sort of like have this third dimension where you put your numbers and so on. Yeah, I believe you can do it, but it's more complicated than just taking powers. So you need sort of like an extra dimension to handle that computational issue. Okay. So this is this. I guess I'm going to take some time on Monday to discuss the singular value decomposition a little bit further, but let's just leave it like this. Singular value decomposition. And this is an idea that is similar. It's an offshoot, basically, of the spectral theorem. It applies to arbitrary matrices, not necessarily square, as symmetric. You take any matrix, and you use this idea, basically, okay? If you start with any matrix whatsoever, A, then if you were to take A transpose A, or A transpose, now you would come up with, so that would be two symmetric matrices that you associated to A somehow. So you can apply the spectral theorem to those matrices and say something about A. You can sort of like translate it back to A. Let me also mention that there's a very popular application of this now, symmetric value decomposition. It's called the principal component analysis. Okay, so this is the underlying math of in principal component analysis. This is especially useful in the context of big data, because it somehow allows you to see sort of like the trends in sort of like a huge data set. So let's start like this. You start with an m by n matrix. Let's call it A. By the fundamental theorem of linear algebra, we have this column space, null space, and so on. And these are orthogonal spaces. So by the fundamental theorem of linear algebra, we have that, so let me just draw it, perhaps. So A is going from Rn to Rm. Let's say that, let's also say that the rank of A, I don't know what the rank of A is, but it is, it's a number, it's R. So the column space of A is R-dimensional inside Rm. Okay, so this is the column space. Now, what is this orthogonal space? Do you remember? It's supposed to be a space here that is orthogonal to this, and it should be given by the fundamental theorem.
It's the null of A transpose.
Yeah. And here you have the column space of A transpose, and here you have the null space of A. So A takes everything on this vertical axis, it's a caricature of course, to 0. A transpose takes everything here on this axis to 0. And further, this is r-dimensional, right, because the rank is r. This is an r-dimensional subspace. This is also an r-dimensional subspace. And really, if you remember the 6, 7, and 8th items in the fundamental theorem, the final version that I wrote, A is an isomorphism of this guy to this guy. They have the same dimension, they are isomorphic, and further, A is an isomorphism from here to here. Of course, it kills everything here, but don't worry about those, just look at this. If you look at only here, it's an isomorphism. So now, basically what I want to do is I want to say something like the spectral theorem. I want to say that A is basically a diagonal matrix up to a change of coordinates. It doesn't quite make sense because A is not even squared necessarily. But what you can try doing is this. You can say, oh, okay, so maybe I cannot find just one matrix as I found here, one Q, such that from the left and from the right, I apply the same thing. That doesn't quite work in general. But what can work is that perhaps you find a Q for Rn and another Q for Rm, different Qs. And so that is the singular value decomposition. Let's think about this. Now, if I were to first apply A and then A transpose, right? So as a matrix, there's this. So A is m by n, which means that A transpose is n by m, which means that A transpose A is n by n, which means that A transpose A is a linear transformation from Rn to itself. And it's a symmetric matrix. Symmetric. So I can apply the spectral theorem to A transpose A, no problem. Can find an orthonormal basis for Rn that is also an eigenbasis for A transpose A. Let me call this basis vectors v1 to vn. And I'm going to do one more thing here. I'm going to reorder these in such a way that the first R vectors they constitute an orthonormal basis for the column space of A transpose. So I'm saying these first R vectors, they should correspond to the horizontal axis in the caricature, and the remainder, whatever the number is, so n minus R, remaining eigenvectors, I want them to be vertical. Okay, so I want this to correspond to the column space of A transpose, which is fine because it is R-dimensional. So I would need R vectors. And here I need, so I have a basis for null space of A. Okay? This is an orthonormal basis with this specific splitting. Now, if I were to apply A to each of these vectors, what's going to happen is this. If I were to apply A to any one of these, because they're in the null space, they're going to vanish. So they don't really tell me much. But these do tell me something. Namely, that the first R vectors in this basis are going to first survive when I apply A to them. And further, and they're still going to be orthogonal. If I and j are not more than r, so I'm looking at the first r eigenvectors there, and I want them to be different, of course. Then if I were to look at their inner product of the inner product of their images, now note, this is the same thing. Let me do this again. A vi transpose times A vj, but this is vi transpose times A transpose. That is to say, this is the same thing as vi against A transpose A vj. But vj is an eigenvector of A transpose A, which means that it's basically Vj up to some number. It's one of these eigenvalues corresponding to Vj. But then this is a number, I can take it out, so I have Vi against Vj. But that basis is an orthonormal basis, which means that that inner product is 0, no matter what this guy is, what this lambda j is. So you see, I start with an orthonormal basis. The first R elements, first R eigenbasis vectors, go to some other orthonormal set of vectors. And they're going to be necessarily in the column space of A because I'm applying A to them. And these are going to vanish. That's not an issue. So this means that this is an orthogonal basis. I didn't say anything about the lengths of these image vectors, but these orthogonal vectors constitute an orthogonal basis for the column space of A. Okay? So this is an R. So once you have an orthogonal basis, you can normalize these vectors to come up with an orthonormal basis for the column space. Now, what is the norm of one of these vectors? Let me just compute the norm squared. Well, this is nothing but A vi against A vi. By the same idea, this is nothing but vi against A transpose A vi, which means that this is vi against lambda I vi, so I can take that lambda I out. So I would have vi against vi. Vi against vi is vi norm squared. But I started with an orthonormal basis, so this is 1. Okay? Which means that the norm of a vi is the square root of this. Okay? And I should also mention that based on this idea that A transpose A is a certain positive definite, so it corresponds to a certain positive definite quadratic form, all of the eigenvalues of A transpose A are going to be positive. So this square root makes perfect sense. Okay? So this is called the ith singular value of A. And it's defined as sigma I. It's almost like an eigenvalue, not quite. In a sense, it's like it's the square root of the eigenvalue of A squared, if you can imagine it like this. A squared doesn't quite make sense in this context, but A transpose A always makes sense. And A transpose A is pretty much like A squared, at least heuristically. Okay, so these are the singular values. And so if I were to normalize my vectors here using these numbers, which are the norms, I would get an orthonormal basis for the column space of A. So ui is going to be A times vi divided by the norm, which is A times vi divided by sigma I. Now u1 to ur is going to be an orthonormal basis for the column space. Yes.
How do you skip minus square root on the
I'm taking the positive one. So this is a positive or non-negative number. Okay, it has one positive square root and one negative one. I'm always taking the positive one.
So how do you justify not taking the minus square root on the I?
I mean, I can just decide one of them, right? I'm saying that the singular values are going to be positive numbers for me, or non-negative numbers at the very least. Yeah.
It's a convention.
Yeah. Singular values are positive numbers. Yes. Yes.
The denominator on that one?
A times vi norm.
Oh.
So I had an orthogonal basis here for the column space. And now I'm orthonormalizing them. Okay. So now u1 to ur is going to be an orthonormal basis for the column space of A. And at this stage, we're pretty much done. So, because in this equation, okay, taking the sigma to the other side, I have this. Applying A transpose to both sides, I get this. But this is lambda I times vi, which is sigma I squared times vi. So that means that somehow, magically, these vectors that I came up with, ui's, are also eigenvectors. Oh, sorry, they're not necessarily eigenvectors, of course, but A transpose takes ui's to vi's. Okay, so ui's and vi's are sort of connected in this way. VI's, when I apply A to any VI, I get a UI up to this sigma I. And vice versa, if I were to apply A transpose to UI, I get VI up to this sigma factor. Okay? We're almost there, but I'm out of time. So we're going to keep continuing. We're going to continue this discussion on Monday. But we're almost there, essentially. All I need to do is to realize that this is a matrix factorization. So ultimately, we're going to end up with this. And we have every single entry here. We just need to figure out how to write it down. Okay? Thank you. I'll see you on Monday.